Thank you for the introduction, Anna. Yeah, I'm very excited to be here today with you. Thanks for attending this webinar. My name is Lourens Walters, and I'm a senior data scientist at Informa. And yeah, as I said, I'm very pleased today to share with you two use cases of generative AI projects that we've implemented in the last 6 months. And the reason for my excitement is really that these use cases would not have been possible to implement was it not for the kind of advances in generative AI that we've seen during the past few years. But apart from that, what excites me about these use cases is not only the fact that they use generative AI to add value to our audience's experience. It's also that these use cases were implemented by using both generative AI and traditional machine learning methodologies, which is something that particularly interests me too. So without further ado, then I'll tell you a bit about Informa. Informa is not the most well-known company out there because of the fact that it's a business-to-business brand, so it typically caters for businesses. So unless you are attending trade shows and events aimed at businesses, you probably would not have heard of the company before. But it is the world's largest event and trade show company. So it's a pretty significant company. It's a FTSE 100 company, and it manages more than 700 brands, which is a lot. So Informa's vision, really, to better understand what Informa does, is to champion the specialist by connecting people with knowledge to help them learn more, know more, and do more. Now, what that means really is it is providing individuals who apply a certain trade in a business with the information and the connections to other people that can enable them to be successful. So with that, Informa has a number of divisions. So to kind of realize this vision, we've got a publishing house called Taylor & Francis. It's an academic publishing house. And then we've got 3 different business verticals that look at exchange of information either via trade shows or via online media, such as a smart event media platform, information, which is disseminated through smart media platforms, and then also web content, mobile, and email. That's how Informa communicates with its audience, and it communicates by more than 600 million audience interactions per year. So it's a substantive number of interactions. So with that background of Informa, so how is it that we thought that how can generative AI enable us to better connect with our audience? And the idea really is to identify the right audience and the right message. So using generative AI to help us to tailor make specific messages to particular parts of the audience. And the 2 problems that we had to deal with is firstly that the data that we collect across the entirety of Informa is non-standardized. So the data captured on the registration sites of the various events are not in a standard format, although we have a standard internal format for content. And then also the information on a lot of the kind of content platforms are typically not tagged, so it doesn't tell you what topics people are looking at. So those are the 2 use cases we're going to look at: mapping the taxonomy or reference data management or non-standardized data, and then also extracting topics from content. So with that, I'll jump straight into the first use case, which is really reference data management. So you can see on the screen there, on the left-hand side, you can see a typical registration page where people enter information. We've got a reference data management team that have a reference data management platform used to kind of map these data elements from all the different registration sites to our internal reference data standard. But it's a very manual and labor-intensive process. And hence they came to us and asked us if there's a way to automate this using generative AI to assist them with this very onerous process. So let's look a bit at what they presented us. So the reference data management team, when they came to us, and when I speak to us, it's the data science team in Informa, which I'm a part of. They presented us with this mapping data set of more than 100,000 mapped labeled records, which we were very excited about because, as data scientists, we like labeled data sets. And this data set really, you can immediately see where the problem is here. In the middle column here, it shows the values that need to be mapped to the target values. And you can see that they're very domain specific. Healthcare professional could be mapped to visitor, guest could be mapped to visitor, business pass could be mapped to visitor. And this is on the left-hand side, is the category audience type. There are more than 29 of these different types of categories that you can map values for. And so we quickly identified the problem that they had in terms of mapping this data is typically the domain specificity that they're struggling with. They tried to map this before using both the reference data. They've got a state-of-the-art reference data management platform that has machine learning built in, and using this, they only gained less than 60% accuracy in mapping this particular data set. They also tried Microsoft Azure AutoML to fine-tune proprietary LLMs within our virtual private cloud, and they attained less than 50% accuracy using this, and then prompt engineering less than 13. They really wanted something more than 80%. So that's when they called us. So what we thought we'll do is take it one step further and go open source and see if we can fine-tune having access to the entire model and all the parameters, the models to a greater extent, and then attain better results. So we went with Hugging Face, and we decided to choose both the 5 different types of models that you see on the screen there. We wanted to go with BERT because it's the state-of-the-art kind of model for text classification. It's a bidirectional encoder, which is very good for classification. So we use that as our baseline model, but the problem is that the context length is quite short for BERT, it's only 512, so you can't really represent an entire website in that. So we also looked at some models with larger kind of context lengths as well as more parameters. So we looked at Llama at the time we started this, and the context length is 4,000 or 8,000 tokens, which is more than large enough to capture a whole website. It generalizes better, but the problem is it's got one directional context attention, which basically it's a generative pre-trained transformer, so it's focused on generating the next element in a sequence of text. And therefore it's not the greatest for classification. But there was a paper published where the causal mask was removed from the attention mechanism in the transformer, which then during fine-tuning caused the model to behave more like a bidirectional LLM, which then results in better classification. So we thought we're going to do this. So there's a paper, I've got the link in the presentation, you can look at that. We implemented this particular method, and we found it to work well in terms of the accuracy we attained. So the process for fine-tuning both of the models that we looked at was really the classic kind of mechanism for fine-tuning large language models. We basically, as you can see there, we took the original transformer and then we froze most of the weights and then unfroze some of them using LoRa, low order rank adaptation. And there's a paper there also that explains a bit about LoRa to you if you're interested. And then we ran the Informa text, the label data set through the transformer with the target reference mapping label data, being at the output. Obviously, we put a classification head on the transformer to then facilitate this fine tuning. So that was the process. So a bit more about our methodology. So we decided to train this on a single GPU, so an NVIDIA A10 running on an AWS instance, and we used the Hugging Face Trainer API because it was something we have used before. It's a very flexible API to use, and it's got good documentation. So for the different models, what we did is for BERT, if you look at the image at the top here, we performed full fine tuning for BERT, where basically because of the fact that there are not that many parameters, about 345 million parameters, the foundation model is represented in 16-bit floating point, a big float, Google big float. It's the kind of standard representation for the base transformer for data within it, and then within the optimizer, you use a 32-bit a float representation, but given that kind of setup, we could fine-tune the whole of BERT, because of the parameters. For Llama 2 and 3, we needed to use LoRa to basically, so again, the base transformer, you still use 16-bit float representation, but within the optimizer, then you only optimize some of the actual weights. The mechanism that LoRa uses, low order rank adaptation. So you use like a linear combination of the weight matrices, the delta of the weight matrices to reduce the size of that matrix, and you then end up with just a subset of the kind of weights that you need to update. So, and you can set different parameters to determine exactly how many like weights you kind of end up updating. So if you start with a small batch size, a low LoRa R kind of sets the order of the kind of the weight matrix that you're going to use to update. And so the lower the R, the fewer kind of weights to update. So we start off with like say 0.1 with like low kind of 0. So the trainable parameters are 10 million and there's 7, so it's 0.1 trainable parameters. And then you see whether you kind of reach the accuracy that you're looking for. And you basically increase these parameters, so increase the number of weights that you fine tuning until your memory runs out, and then see if you can reach the accuracy that you're looking for. So we didn't, so we had to go onto QLoRa, which basically then extends the LoRa paradigm. What it then does is it also takes this base transformer where you've had the 16-bit big float representation, and you then use a 4-bit representation for the base transformer. And using this kind of quantization method, we up the trainable parameters to about 90 million, and it's about 1.2% of the parameters. And at this point, we basically gained stability in the training. So if you look at the learning curves here for Llama 3, you can see that below about 10 epochs, there's a stable kind of learning curve in terms of the loss. And the accuracy that we attained with Llama 3 was also more than 80%, which is what we're looking for. If you also look at the accuracy across the different categories, it's fairly consistent above 80, which is also what we were looking for. So we were quite happy. Rolling out this model then was also fairly easy. You just need to write the code to basically tokenize input data and then present it to the model that you've then instantiated. And then you can basically obtain the logits and then create from the logits the probabilities for the predicted classes. And so here's a few examples of us kind of applying this model to test data. And you can see that the ATX West that we looked at previously is correctly classified as visitor. And in this case, all access pass is incorrectly classified as delegate notice. So there's still some inaccuracies, but the accuracy is good enough to kind of deploy, and it's not very costly to deploy. I'll give you some costings later. So that we were very pleased with the fact that we could get Llama to classify accurately, using a kind of a causal mask that updated the attention. So the second use case that I want to talk to you about is just as exciting as the first one. It's really about the problem that we had with automated text extraction. So we've got more than 700 brands that we support. Each one of these brands have a web kind of product, so website, and these websites have hundreds of thousands of web pages. They don't always have tagged content. So what we're looking at is a way to extract for every single web page the topics that page kind of speaks to. So the challenge with topic modeling is really that it's very domain specific. So for each of the different brands, the topics differ quite substantively. So using an LLM, you typically can't extract topics that are specific enough for the various different verticals. So, and you also want, the other problem is consistency over time. So using an LLM, a proprietary LLM to extract topics, the topics change over time, and you really want topics, you want to look at trends over time. So you want a mechanism to extract the topics, but that for them to remain constant with you, possibly adding a few more over time as you go on. There's some other kind of limitations too, but the gist here is that LLMs is not a solution on their own for this product. So the solution we came up with looks quite complex. It's this. So it's a hybrid approach of using both LLMs and traditional NLP. Now, this framework is really based on BERT topic, so that Martin Grootendorst published. So there's a link here. You can read all about it here. So we took his framework and we basically extended and added a few things to it. But we'd like to talk you through this today. And the gist of it really is that you've got the web pages on the left-hand side here, and the web data goes into this model and out comes the topics on the other side. And it's a fully automated process. To give you an idea of how this process works, I'm going to talk through this, a little bit during the talk. But in essence, what happens here is that for every single website, we can call it a document, also a website's document, in the kind of the phrase that I'm going to use is that we take the website or the document, we then extract embeddings for that website. So these embeddings are large language model embeddings. We then take those embeddings and we dimensionally reduce them because they're very high dimensional, these embeddings for these websites. We then cluster the embeddings for the websites. And we then hope that the clusters would contain similar topics because of the fact that the large language model embeddings contain meaning as it is contained in the text. Once we've clustered these documents and found that the topics related to these clusters, we then need to know what these topics actually mean. So we derive what words these actual topics consist of. Once we've got the words the topics consist of, we obtain topic descriptions by running it through a language model. Once we've done that, we assess the final topics and see if some of them need to be combined or not because they're similar. And then we create a final classifier, a text classifier that when given some websites, it can produce a list of topics. So that's the overall kind of like process that I'd like to talk to you about. So the first thing I'd like to talk to you about is this first step here, is extracting the embeddings. So the problem we have here is that the embeddings for a typical large language model is not domain specific. And what we want to do is just create a way to make these domain specific. And the way we do this is we first run an LDA model on it, which is a latent data allocation model, which is a traditional ML model for extracting topics from a corpus. And we then use these topics extracted from LDA to update the BERT embeddings. We only run this model once, and once we've got this LDA model for future instances of this model, we can always add these LDA topics to the BERT embeddings to create the context-specific embedding. So yes, just so an idea. So for aviation, we've got say 250 web pages, on average around 350 words per document. The pages look something like this. We run LDA on it. We optimize some parameters. We test whether it kind of captures the topics. So we do internal and external validation. So there are some coherence and perplexity measures that we use to see if LDA worked, and then we also use subject matter experts to validate whether LDA actually captures the domain. And they gave a good score to us, which means that we used LDA. So the way we then what we do is we take these LDA. So if you look at this image on the right hand side here, we then, as I mentioned, combine the topics for LDA and the BERT or Llama embedding. So what I mean by that is if you've got, say you've got a document, say this is a website, say S1 is a website. So you run the topic model on S1 and you find the words that represent that website. You also run that website through BERT, and then you find the last hidden state in BERT is the C. So you find this representation that BERT presents of the website, and then you find the topics that the LDA topic model, and then you combine them into a new embedding. So you can do that by various ways, taking an average, or you can concatenate them. You can take a weighted average. There's an article here that you can read if you want more detail on that. We used a weighted embedding, but you can experiment and see what works for you. So then what we did is we looked at the kind of results that this kind of method generated. So again, we asked our subject matter experts, before kind of joining the LDA with the BERT embeddings and after, do the topics look better or worse? And they were in favor of the more domain specific topics. And then also, if you look at clustering kind of internal metrics such as the silhouette score, so a higher score closer to 1 is better. And if you look at the silhouette score for the clusters of topics for BERT and LDA, you get a higher score, it's 0.75, 0.767 if you only use the BERT embedding. So it definitely did seem as if the domain-specific embeddings were working. So this next step is you cluster these embeddings to obtain the topics. So you firstly dimensionally reduce them, and then you cluster them to obtain the topics. So for this, we used a dimensionally reduction mechanism called UMAP. experimented with a few parameters, found what worked, and then we used HTTP scan for clustering on top of UMAP. And as you can see here again, if you use the bird clusters after kind of clustering bird, it looks fairly good, but here if you use the bird and LDA kind of clusters, you get much better kind of clusters of topics out there. So that's then how we obtained the topics, by clustering these embeddings. The next thing we want to do is extract the actual, for each of these topics. So, we've obtained these clusters of documents that we, ascertain to be a topic, and we want to basically a description of these topics, because we don't know what it is. And so how we obtain that is basically, firstly, we use an algorithm also developed by Martin Grootdorst that's called CTF-IDF. And what it in essence does is TF-IDF is an algorithm which finds the most important words in a document, in a corpus of documents. But what TF-IDF does is it finds the most important words in a cluster, in a corpus of documents. So if you look at it over here on this image, on the left-hand side, these little circles indicate the different topics. So they're these like clusters of topics that you see there. And here you see topic number 2, and these are the words that we found via CTF-IDF that are the most important in this actual topic. So so the next step, what we then do is we use a language model. We present it with the 5 most relevant documents of this actual cluster, of this topic cluster, as well as the top 10 words. And then we hope that it'll give us, kind of clear explanations of what the topics actually are. And surprisingly, it works. So this is kind of a map plot of the topics that we obtained, and you can see airline routes and traffic, space exploration, airport facilities. So they're all sensible topics, and we have validated these with subject matter experts. So the last and final part then is really to take these topics that we've extracted and to ensure that they're consistent, and then to find a way to create a classifier that we can easily kind of classify future documents in terms of what topics belong to those. So so what we used for this is that the topics that we found came out. Sometimes you find topics that are similar in nature to each other. Those topics, obviously, if you calculate intent based on who's viewed the different topics, they'll dilute the intent if you've got people viewing things that are similar. So you want similar topics to be kind of combined. So what we did is we used hierarchical clustering to cluster those topic vectors and the descriptions via CTF-IDF. So here you can see it's hierarchical. So we use linkage function of WAR, dissimilation for cosine. So the cosine dissimilarity is indicated by the length here. So you can see the topics that kind of like are grouped like closer on the left here are the ones that can possibly be combined, or the ones with very short dissimilarity along the horizontal there, like here, or there. So those topics can typically be combined, and you can decide where to combine them. And then you can recalculate the actual CTF-IDF vectors that kind of explain what those topics are. So you get like combined topics, so you can get more consistent kind of descriptions of your topics. So this is what we then did, and then after this, what we do is with the final set of topics allocated to the clusters, we then build a classifier. So basically, use a large language model. As with the taxonomy use case, we basically train this classifier to predict. So it's a multi-label classifier. So it basically classifies several topics per record. So what we did is when we did this is we trained on 150 topics on an average. So 3 topics per document, and we had a C statistic of more or less 72%. So just in terms of how much it costs to do this kind of like topic model fine tuning, you can see that to build this classifier, it took us with BERT about 1 hour of training time, which cost $2, and with Llama a bit more than a day, 24 hours, so a day and 4 hours, and it cost about $70 to actually build the model. Then to infer the topics is very cheap. So for 2000, the test set had about 2000 records in it. To run the whole test set through takes about 15 seconds. If you use Llama on an NVIDIA A10, which is a pretty large machine, it's about 60 cents. So, inference is really cheap, using this model. So then just some other approaches. So to note is that there's a lot of work being done in variational autoencoders in terms of topic modeling. This is a different approach to what we followed, but it's gaining a lot of traction. And then there are taxonomy-based approaches. So using existing taxonomies as OpenAlex or IAB, it's a concept taxonomy or marketing taxonomy, and then creating graph representations of these taxonomies. And you can use these representations to either predict, what topics are in corpus, or you can use it to manage and identify new topics or merge topics. It's a powerful kind of mechanism, and it's used with great kind of success in many different fields. It's something that we certainly are looking at, using in future. And you can also model hierarchical taxonomies in this way. So what we've achieved really is just to use LLMs in combination with traditional LLM to classify short text to large number of classes for automatic reference data management mapping. And then we also used these domain-specific contextualized embeddings to identify latent topics and corpuses, to create meaningful topic descriptions using the conversational LLMs, and then to manage the topic taxonomies through semantic textual similarity merging. So, and potential future uses that we'd like to use this for is to also embed the audience into the same kind of embedding space, and then to find, which people are interested in which topics, in order to gain a deep understanding into audience interest. And that's really it from my side. I hope there are some questions. I don't know if there's time for that.
Yes, we still have a few more minutes. So if anyone has a question, please leave it in the Q&A channel. I shared the link in the chat on your right.
Anna, if there are any, if you can read them out, because I don't know if I can see. Wait, I think I've got them here. Okay. Is it under my? Okay. Is it under Lourens Walters there?
Yes. Here
okay. Yeah. Please ask me. I see Anastasia. That's good. Hi, Lourens. Could you please share the link to the 2023 paper about? Yeah. Can I share it here, Charles? Yeah, certainly, Charles. I'll do so after. If I do it now, I'm going to get distracted if there are any other questions. But I'll serve it on here for you, Charles. And just to say about that, the guy's name is Sean Lee. He's from the Hong Kong Polytechnic, and I actually contacted him, and he assisted me personally with getting this to work. So he's very helpful. So if you read his paper, also reach out to him on LinkedIn, and also GitHub. He's on GitHub, and he's got questions you can answer about the model. If you struggle to get it working, he certainly helped me to kind of get this working. So I'll share that link, and do use it and reach out to him. Then let's see. Okay, Alexandre, he said, can you please expand on the problems, deficiencies with providing a list of topics to an LLM? Example in the prompt, and then the LLM is asked to classify the input. Okay, good question, Alexandra. Okay, so I mean, in essence, okay, great, thanks, Charles, for that. Okay, so Alexandra, it's very, very, very good question. Okay, so that's one way of doing it, is that if you have a, if I understand your question correctly, what you're asking is if you've got a taxonomy, is if you provide in a prompt the taxonomy to the actual LLM and ask it to either, and then send it a document and ask it either to classify the document according to the taxonomy, or otherwise, if you, the alternative is to just give it the document and to tell it to come up with the topics itself. Okay, now I mean there's several kind of problems that we found with those two different use cases. The one is that if you provide the taxonomy, it's a very large taxonomy, as well as the document, you often have limited, you run out of like tokens to sufficiently explain both the taxonomy as well as, you know, to provide it. If you've got very large websites with a lot of text, then you can very often run out of you know, tokens. So that's the one problem. The second problem is that being a large language model, it won't always return. It might even return, even though you gave it the taxonomy, we found that it often returns classifications outside of the taxonomy. So you need to do some post-processing to clean up the results, because it's a large language model, and we all know it's a probabilistic model, and it's not going to generate, you know, something exactly the way you want it. So there's some cleaning up. If you, so which, you know, if you have a classifier, you don't have that problem, because you've built the taxonomy and it's going to classify what you tell it to. So those are two problems. Other problems are that, you know, in terms of managing topics over time, you know, you're dealing with an external kind of API, and, you know, they can change it. So if you ask for a topic today and you ask for a topic tomorrow, it might be different. So, you know, unless you manage that kind of large language model yourself, you know, that obviously kind of, you know, could be a solution. There's also cost. I mean, like you saw with our classifier, I mean, like our data engineering team actually implemented our classifier on a CPU-based machine only. It takes a bit longer to classify, but it's dirt cheap. So in terms of if you've got a lot of topics you want to classify, then, you know, going with a classification model kind of will help you. So I don't know if that kind of gave you some kind of idea, Alexandra. There's some other kind of things I can talk to too, but I think let's see if there's another question I can talk about. And certainly, Alexandra, you feel free to catch up with me afterwards, or, you know, ask questions here. I'll try and answer them afterwards if you have any. So great presentation. We are dealing with similar problem on second use cases. What was the most challenging component? Web scraping, extraction. Great question, Robert. So I think that's a very difficult. So across the company, I mean, we're waiting. So to get the web scraping is a problem. So I mean, we're currently waiting to implement. So this is not in production. The taxonomy use case is in production. So we've got that running in production. That was quite quick to roll out. The topic modeling has not been rolled out. We're hoping to roll it out by December for a specific use case. And what's holding up the rollout is the web scraping. So it's the data, it's the pipeline to get the data so that we can actually map the data consistently. So the data engineers are kind of struggling with that consistent pipeline. But apart from that, I mean, building the model, which is what I did, the model evaluation to me was difficult. I dealt with, you know, several small subject matter experts on this, and depending, you know, on you know, how proactive and how knowledgeable the people are, you can struggle. So I found and also your feedback might differ substantively from one kind of like you know, set of users to another. So kind of consolidating that and deciding on, you know, what makes the most sense was quite a big task, I would say. And then I think, yeah, I mean, in terms of the technical part, you know, there were challenges. So you know, just from a coding perspective and testing, you know, rerunning the model to kind of, so that process of kind of running and failing until you find something that works. Initially, there, you know, were frustrations around that, but that's something you can overcome. So thanks for that question. How well does this method translate to technical text rather than general text? Would it be expected to perform less well if the language has many technical terms? Yeah, that's a very good question, Sean. What we have found is this works the domain specific kind of version of it works surprisingly well. I mean, it like some of the subject matter experts, when we showed them the topics it comes up with, a lot of them were actually surprised because their internal kind of content management team said they didn't actually know that they were writing articles on this, and when they were actually like looked at the content that they had, they said, you know, they actually saw that, you know, these topics actually do come up. So, you know, both from a, you know, an audience perspective as well as from a content kind of generation perspective, you know, it's a valuable kind of exercise to go through. So from our perspective, it worked on technical texts very well. But the hierarchical, the graph-based approach, which is an extension to this work, other parts of our business in the publishing side, the technical publishing, they use the graph-based approach where you basically have a taxonomy that's in a graph, and you extract like from the graph embeddings. So your embeddings come from the graph rather than you kind of extracting it from the LLM straight. And that kind of process, like they have great success with, in like they match like authors to so they look at all the different authors that have cross-cited and referenced technical kind of papers and stuff, and they try and find the best people to go to kind of be reviewers for journal articles, and in that technical domain, the use of graph-based large language model embeddings work very well. So that might help you too. Yeah, I can see the complexity of the solution components. Thank you, Lourens, for sharing. Okay, great. No, thanks, guys. Yeah, so Robert, I think you made a good point. I think operationally to roll out something like this has challenges. Also, I found, apart from creating the model, I think the model is the easier part actually. but yeah, so thanks for that. And thanks, Sean. I hope that helped you too. But feel free to reach out and ask questions.